This is the fourth computer session where we are slowly evolving a one-dimensional finite difference time domain code into something that's rather feature-rich and complete. To remind us where we were from last time, we added the perfectly absorbing boundary condition. So when we inject a Gaussian pulse, when that hits the edges, it just keeps going. And what we're looking at here appears to be a reflection, but if we look at the amplitude, we're 4 orders of magnitude down. We're automatically scaling the y-axis. So in fact, this is working rather well. So what we'll do now is we will save this as step 4. And we will proceed, and we'll change our comment here to add total field, scattered field source. And we'll change this nlam parameter back down to 10. Well, let's make it 20. Let's look at what happened to the pulse. We have this pulse that we're putting in the middle of our grid, but it goes in either direction, and we're not controlling it very well. What we would like to do is inject a one-way source. And so what we'll see is this Gaussian pulse, just sort of half of it appears in the middle and launches in one direction. And so we're controlling it better, and that's much better able to simulate devices. Because if we're trying to record reflection, we run into another problem. How do we tell the difference between what gets reflected from a device and what just happens to be traveling backward from our source? Okay, so most of this code is the same. We don't actually change anything in this code until we get to where we're calculating the source. So let's scroll down there. Okay. We've calculated the electric field source. I want to remind you the assumption here is that you've looked at the theory slide, so you understand here when we're doing a total field scatter field source, we need both an electric field and a magnetic field component, and they're slightly skewed from each other. So all we have to do here is calculate the magnetic field source as well. So it has an amplitude, and it is negative square root ER NZ source over UR NZ source. So that will be the amplitude. The electric field amplitude is 1. The magnetic field has a different amplitude simply because it can be inside of a material, and the amplitudes of E and H need to be balanced, taking into consideration the material impedance. So that's what that does. Now we calculate the H field source. And that's A times, and then another equation for a Gaussian. Get the minus sign in there. So at this point, other than the amplitude term, it looks the same as the E source. But remember, there's a skew or a delay. So we have to add this little tiny delay. We'll just call it S for lack of anything better to call it. And let's calculate that. And the reason we need the delay is because the electric and magnetic fields, they're a half time step apart. They're also a half grid cell apart. So this S accounts for that delay. Let's take a look at these two, and let's plot them. So we'll plot T, E source, and we'll do this with a solid blue line. Let's go ahead and run it and see what we get. So that is our E field source. Let's go ahead right over top of that and plot our H field source. We'll need to use the hold on and hold off commands to superimpose these. H source, and we'll make the H field a red line. Let's go ahead and plot them now. They're inverted. Now what I'll do is I'll plot the negative of the H field, and that will bring it up to overlap the E field. So we'll get a better idea of the skew between them. So let's just invert the magnetic field artificially. And let's look how similar or different they are. Let's make this bigger. Notice they almost lie on top of each other, but that S does introduce a delay. Let's zoom in, the very peak, where it's most apparent, and we can see this tiny little skew. That's that parameter S, because they're a half time step apart and a half grid cell apart. Okay, so we will delete this code. We don't need to see them. I just wanted you to see that. Okay, so all we've done so far is add the H field source. We now have to go into the main loop of fdtd and modify what we're doing there. So we could do it before or after we record the field, because injecting the source won't be changing the boundaries at all. So let's do it before we record H field at the boundary. And we'll call this H source. So notice right away it's looking like a soft source, in that we're taking the H field, we're taking whatever the value is and correcting it with something. And if you've worked through the theory slides and listened to that, that equation should make some sense to you. It's the correction term that we pulled out of the procedure when we did the total field scatter field. So that takes care of the H field source. Let's go down right after the update and do the equivalent for the E field. Then we also need to remove our old source, our crude source, down here. We really just put that source in just so we could throw some power into our grid and we could watch it hit the boundaries. We could get our perfectly absorbing boundaries working. We don't need that now. We're doing this differently, so be sure to delete that. A few things I want to point out. We're updating the H field to inject the source, but notice we're using the E field source to do that. And down here, when we're doing the source on the E field, we use the H field source. It's tempting to use E source here and H source up here, but don't do that. So this is the correct way to do that. And that just comes out of the equations when we applied the total field scatter field concept to Maxwell's equations and pulled that correction term out. Let's watch what happens now. See if we've made any typos or anything. Okay, we're generating a pulse, and notice it just goes from left to right. We're seeing what gets reflected, but we're 4 orders of magnitude down. So that is it. That is our total field scatter field source. We could move it around and inject in different places. We would just change NZ source. Let's divide NZ by 4. So the source should enter a little bit to the left now. And notice nothing propagates backward until it reflects off the edge. So if we're trying to record reflection from a device, we don't want anything to come backwards from the source. So that's it. We now have a one-way source, and we did that using the total field scatter field technique.